Assalamu alaikum wa rahmatullahi wa barakatuh. At the beginning, I would like to thank you all for listening to my presentation today. My name is Al-Sami. My GS number is 56391. My topic is performance enhancement of optical transmission system using stimulated Brilliant scattering, SPS. My supervisor is Dr. Zuhaida Zan. Background about optical communication and OFDM. Optical transmission system use the optical medium to transfer the optical signal from the transmitter to the receiver with a minimum level of distortion. OFDM is commonly used technology in the modern wire and wireless communication system. Development of optical communication system design is performed to carry high capacity of transmission rate or the data rate to reach long distance, which is influenced by economic growth. OFDM is robust solution to simple interference and high spectral efficiency and strong immunity. OFDM can be implemented in the optical domain as a coherent OFDM, direct detection OFDM, and self-coherent OFDM. Problem statement. Self-coherent system has been reported to provide a simple design with a low implementation cost than coherent OFDM system. However, the system require some number of null or zero OFDM subcarriers to accumulate a filter response or bandwidth in order to extract the optical carrier at the receiver. Thus, the main challenge of this technique is to reduce the gap or the number of zero subcarrier between optical carrier and subcarrier in order to increase the spectral efficiency. Thus, the main challenge of this technique is to reduce the gap or the number of zero subcarrier between the optical carrier and subcarrier in order to increase the spectral efficiency of the system. The self-coherent OFDM require a very narrow optical filter to accurate and precisely filter out the optical carrier from the signal to avoid the leakage and reducing the zero OFDM subcarriers, which increases a bit error rate and reduces the spectral efficiency. Moreover, narrowband filtering is necessary to defeat the noise around the optical carrier and boost the carrier to noise power ratio and optical to signal to noise ratio, which improves the system performance. Narrowband filtering and amplifying based on SPS offer a suitable solution for extracting and amplifying the optical carrier. SPS has a narrowband filtering feature at about 10 MHz and wide. Furthermore, SPS amplifiers provide a very high gain with a very small input signal. SPS amplifiers are low cost, low noise, and suitable and reliable optical amplification solution. The aim and objective of the report: to develop the self-coherent OFDM transmission system, to apply the SPS into a self-coherent OFDM self-heterodyne system, and analyze the system performance with the SPS. The project scope are OFDM signal generation and demodulation using MATLAB, co-simulation of MATLAB into VPI transmission maker, development of self-coherent optical OFDM transmission system using VPI transmission maker, implementation of SPS amplifier and filter in VPI transmission maker, adaptation of the SPS amplifier into the transmission system using VPI transmission maker, and finally analyze the system performance with the SPS. Literature review. In our report, the following headlines have been covered: the optical OFDM, current optical OFDM, direct detection OFDM, self-coherent OFDM, self-heterodyne optical OFDM, and self-homodyne optical OFDM. Moreover, the SPS has been explained how can we take the advantage of this effect and use it to design a filter and amplifier. And lastly, the related works have been covered. OFDM is used intensively in optical communication system. It can handle sizably volumes data transferring and has a strong immunity to coherent dispersive. The general design of OFDM is shown below. Optical OFDM in general can be implemented in coherent OFDM and direct detection OFDM. Both of them has benefits and drawbacks. For direct detection of DM is simple and low cost, but it has a limited capacity, so it's a suitable solution for low cost application. Current OFDM, on the other hand, is a high capacity, high sensitivity, but it's complex and costly because it's required a complex DSP to compensate phase noise and narrow laser oscillator on the receiver side. Self-current OFDM is an alternative technique for coherent OFDM. This technique retrieves the phase information and frequency directly from the carrier without employing neither phase noise compensation nor local oscillator on the receiver side. Self-coherent is simple, high capacity, low cost, and high sensitivity, but it requires a narrowband filter to extract and amplify the carrier from the received signal. Generally, self-coherent OFDM can be implemented in self-heterodyne and self-homodyne. Simulated binaural scattering is an optical resonant non-linear effect which happens within the optical medium, cause a scattering for the optical pump light in the backward direction. It limits the power of the pump optical that can be sent through the optical link. So when the power of the transmitted signal or pump signal reach a specific level, this effect will be stimulated and affect the management system. Stimulated binaural scattering can be employed to design a filter and amplifier. SPS is commonly used for light amplification in some fiber optical system, has a gain bandwidth about 10 MHz, gain exceed 40 dB. SPS optical filter has a tunable range of 50 MHz to 4 GHz with a 15 MHz of a tuning resolution. The selectivity gain improves was more than 40 dB with extracting a line width window of 10 MHz of line width tunable passband feature. Related work, many solution has been proposed to enhance the self-current OFDM by using different methods. But for our project, we will employ the SPS-based filter and amplifier to enhance the system. Methodology. In the work, the self-heterodyne has been implemented and evaluated. The key component in the work and the design was using the SPS filter and amplifier. The feature of SPS can be held to reduce the gap between the carrier and subcarriers, and as a result will enhance the overall performance of the system. The basic design of our system is shown in the figure. We will employ the SPS block in the receiver side in the carrier path to extract the carrier from the received signal and amplify it and use it as a local oscillator. SPS filter and amplifier design. The main goal for our work to enhance the performance of the optical transmission system by taking the advantages of the optical filter amplifier that is based on the SPS. We adopted to enhance the performance of the self-coherent, self-heterodyne optical OFDM. We applied the SPS to improve the OSNR and bit error rate for the received signal. The theoretical analysis of the design has been performed and showed that the OSNR could be improved by tens of decibels. SPS operation concept. The diagram shows the design of the SPS-based filter and amplifier. We will use this design and implement it in VPI transmission maker to extract the optical signal for the carrier and use it in the receiver side. Result and discussion. In this chapter, the self-heterodyne optical OFDM transmission system is developed and analyzed. The analysis includes the investigation of the evaluation and application of the SPS filter amplifier and the self-heterodyne optical with several laser line width and fiber lengths with different scenario of M size QAM modulator onto the OFDM subcarriers. The system evaluation was depending on the bit error rate, OSNR, gain, and kernel installation diagram. The actual implementation of transmitter side and the transmission link in VPI environment. This figure shows the real implementation of the system in the VPI environment. This is the transmitter side. This is the transmission link. The OFDM signal was generated by using MATLAB and by using this component, read file component. The I and the Q signal were loaded to the VPI. This component was used to were used to convert from digital to analog signal. The IQ modulator here was used to convert the signal from the electrical domain to the optical domain. The optical amplifier with the gain controller here was used to compensate for the noise that was generated by the IQ modulator. And the transmitter link was two spans of optical fiber with 100 kilometers for each, with two optical amplifiers. These are IQ signal in the frequency domain and time domain. This is the transmitted signal from the transmitter side, as you can see here, by using virtual carrier technique. This a spectrum here with a resolution of 2 megahertz, and the spectrum here with a resolution of 12.5 gigahertz. OSNR has met by using SPS. The actual implementation of SPS in VPI environment. The figure shows the actual implementation of the SPS filter amplifier in the VPI environment. The bandpass filter here used to separate the carrier from subcarrier, as well as to reduce the noise. P1, P2, and P3, and P4, and P5, and P6 represent the measuring point. We considered this point to evaluate the performance of this component. This is the spectrum of the carrier after extracting it from the subcarrier. This figure obtained in P1 here. As you can see here, the OSNR was 40 dB. This is the spectrum of the signal obtained at P2. As you can see, there is upper sideband and lower sideband for the signal. The reason for existing the upper and lower sideband in the actual design of the SPS component, there is a function generator here used to drive an MZM modulator to generate this upper and lower sideband. The upper sideband and lower sideband will beat with the stock and anti-stock signal in this component. The purpose of generating upper and lower sideband is to generate seeds with the same value of Brilliant shift, because when the SPS effect generated, the stock and anti-stock signal will be shifted from the original signal by 11 gigahertz. So the upper sideband and the lower sideband will beat and interact with these signals. Also in this figure, a second and a third harmonic signals is appeared here. This is a carrier after filtering it by using the bandpass filter in P4, as we see in the figure here in this area. The signal was amplified by optical amplifier and get gain about 3 dB and get gain of 3 dB. This is to use it to stimulate the Brillouin scattering effect. This is the EDFA gain. This is the output signal at the 0.6. 0.6 represents the output. 0.6 represents the output of this component of the SPS filter and amplifier. As we can see here, the lower sideband and the stock signal were located in the same position. Because the stock and the lower sideband were separate in the same direction, so the output signal will be amplified. The output signal at point 6, the OSNR at this point was 67 dB. The effect of bandpass filter on the overall power gain of the SPS. The figure shows the power gain against the bandpass filter. When we increase the bandpass filter, the power gain of the output increases. SPS amplification gain according to the fiber length. The figure shows the power gain against the transmission distance. As we can see in the figure, there's a little degradation in the power gain when we increase the distance between the receiver and transmitter. There's very little degradation because the pump signal in the SPS block was amplified with a 1 watt of power. That's when we increase the distance. Attenuation of optical link will not affect the power gain in the system. OSNR performance of the system. As we can see in the figure shows the value of SNR against the fiber length. As we can see in the figure, the value of SNR remain unaffected due to the attenuation generated by EDFA and remain constant in the receiver side. SPS input signal with output signal. This figure shows the input and the output signal of the SPS amplifier and filter. As we can see here, the output signal is shifted by minus 26 gigahertz from its original from the center of frequency, while the carrier was shifted by only minus 15 gigahertz from original place. So to take the higher advantage of this component, we have to shift the output signal and return it to original place in order to demodulate the signal in the receiver side correctly. The figure shows the output signal of the SPS after using the frequency shifter. We have implemented two cases to get consolidation diagram and bit error rate with and without frequency shifter and compare the results. This is a consolidation diagram by using frequency shifter and without frequency shifter. As we can see here, without using frequency shifter, we can now demodulate the signal correctly, while when we use the frequency shifter, we get a perfect consolidation diagram. Moreover, we have changed the laser line many times to get a different consolidation diagram by using frequency shifter and see the effect of the line width of the laser. So as we can see here, when we decrease the laser line width, we can get a perfect consolidation diagram. Moreover, when we use a high order of modulation format, it's highly affected when we increase the laser line width. Bit error of self-heterodyne optical OFDM. This figure shows the bit error rate with fiber length for two cases by using the frequency shifter and without using the frequency shifter. Without using the frequency shifter, the system suffers from high bit error rate. This is because the received signal cannot be demodulated correctly. And when we use the frequency shifter, we get a correct value of bit error rate. Also, when we increase the length of optical link, the bit error rate increase. That's because when the fiber length increases, the attenuation increases. Also, the chromatic diversity carrier and subcarrier uncorrelated, which increase the bit error rate. Conclusion and future work. In conclusion, the self-coherent OFDM was successfully developed by adopting the SPS filter amplifier and showed that the system OSNR could be enhanced. The SPS-based filter amplifier was successfully applied in the self-heterodyne optical OFDM and showed good performance The performance of the system is successfully analyzed and evaluated according to the OSNR and oscillation diagram and bit error rate, and has shown that the overall performance increased when the SPS-based filter amplifier used the X-driver carrier. The practical experiment shows that SPS could be enhanced the OSNR of the system by more than 26 dB. Moreover, the SPS-based filter amplifier have the ability to be tuned to use at any frequency of laser source. This feature gives it flexibility with work in different conditions and scenarios. The output signal of the SPS block was shifted by minus plus 11 GHz from the original place. Therefore, to take advantage of this component, a frequency shifter has been employed to shift the output signal to its original place. We have implemented two cases of shifting and without shifter without shifting the output signal and compare the result in order to be more understand about the SPS work and the effect. The future works of this study can be investigated in the term of develop the SPS-based filter amplifier, apply the SPS filter and amplifier in different optical transmission system and compare the result and enhance the gain of the OSNR of SPS-based filter and amplifier. This is the reference of our study. Thank you.